So far, we've just been talking about limits where x approaches a finite value. But what happens when x goes to infinity? So the limit as x goes to infinity of this function can also be thought of as the end behavior of the function. So this is asking, what happens as we move further and further along the x-axis to the right? For example, let's just say that this function decreases forever to 0 as x grows larger and larger. So then we can say that the limit as x goes to infinity of this function is 0, since that's what it approaches as x approaches infinity. And for a function like this, where we see that as x increases, f of x also just increases, we can say that the limit as x goes to infinity of this function is infinity. And if you have a function like this that tapers off not to 0, but to some finite value L, then we can just say the limit as x goes to infinity is L. And this should look familiar because you should have seen it in a previous math class. This line y equals L just represents the horizontal asymptote of this graph. So we say if the limit as x goes to infinity of this function is some finite number L, then y equals L is a horizontal asymptote of your graph. So if you have the limit as x approaches a finite number equal to infinity, then that indicates a vertical asymptote. But if you have the limit as x goes to infinity equaling a finite number, then this is a horizontal asymptote. And an important thing to note is that we can't just do arithmetic with infinity. But when we're solving a limit, we still want to be able to direct substitute with infinity. And to do so, we're going to take advantage of this limit right here. So this reads, the limit as x approaches infinity of any constant over x to any power greater than 0 is equal to 0. This makes sense because we know that we have a constant up top and a power of x on the bottom. We know that for x raised to any power n, we know that this will always increase as x increases. And by the way, this restriction is only so that this doesn't just go to the numerator, because then this limit will equal infinity. So we're growing x to infinity. And so if we take a constant and divide it by x to any power n, then we're dividing c into more and more slices as we increase n. And if we want more and more slices out of a set value, then those slices have to get smaller and smaller. And as we approach an infinite number of slices, the size of the slices has to approach 0. And for any value c and n, this graph will always have this general shape. And so we can also graphically see that as x approaches infinity, this has to go to 0. That fact comes in extremely useful when we're solving limits of rational functions like this. So if you try to go ahead and direct substitute infinity into here, then you just get infinity over infinity, which is an indeterminate form. And this is one of the many reasons why you can't just do arithmetic with infinity, because most of the time it leads you nowhere. So how I'm going to solve this is I'm going to multiply the top and the bottom by 1 over x squared. Like so, and this gives me this. And this is where we use that fact we discussed earlier. We know that the limit as x goes to infinity of c over x to the n equals 0. Also remember from the limit properties that we can just distribute this limit to every term in this fraction. We're going to go ahead and evaluate the limit of each of these terms one at a time. So here there's no x's to grow to, so the 1 stays. And here we have c over x to the n, where c is 3 and n is 1. And we know that this goes to 0. And here c is 1 and n is 2, so we also know this goes to 0. This has no x's on it, so this stays. It's the same deal with these two. These are both in the form c over x to the n, and we know that both of these go to 0. And by doing that, I get that this limit is just equal to 1. And we wouldn't have been able to solve this limit without using that fact from earlier, showing why it's so useful. But there are shortcuts to solving these kinds of limits, and these are all derived from using this fact. There are 3 kinds of rational functions that you can encounter. First is when the degree of the numerator is greater than the degree of the denominator, and in that case, the limit as x goes to infinity of the rational function is just infinity. And that makes sense because what this tells us is that the gap between the top of the fraction and the bottom of the fraction increases as x goes to infinity. So if the number being divided outgrows the number it's being divided by, then that ratio has to go to infinity. Reversely, if the degree of the numerator is less than the degree of the denominator, then the limit as x goes to infinity of the rational function is just 0. So just like this tells us that the gap between the numerator and the denominator increases as x goes to infinity, but this tells us that the denominator is bigger. If what you're dividing by is bigger than what you're dividing, then that ratio has to go to 0 as x goes to infinity. And the third case is when the degrees of the numerator and denominator are equal. If that happens, then the limit as x goes to infinity of the rational function is just the ratio of the leading coefficients. The problem we did up here was a type 3 rational function, which means this limit is the ratio of the leading coefficients. And we see that the leading coefficient here is 1, leading coefficient here is also 1, and 1 divided by 1 is 1. And this is true because if the degrees are equal, then that means the top and the bottom grow at the same rate, preserving the ratio that they started with. To close the video, I'm going to do these 3 examples for you, and each of them cover a different way of finding a limit at infinity. This problem is the same kind of problem we looked at in the last example. And using the shortcut, we know that since the degree of the denominator is bigger than the numerators, this has to be 0. But we're going to show the work. I'm going to start by multiplying the top and bottom by 1 over x squared. So we always want to multiply the top and bottom by something that'll make the leading term in the denominator 1. The rule to follow is you should multiply the top and the bottom by 1 over x to the degree of the denominator. The reason is, if we went any higher than 2, all three terms would be divided by x to some power, and so all of these would go to 0, and we'd have it divided by 0, which we can't have. If I do this, then this simplifies to this. And we know that we can apply the limit as x goes to infinity onto each term separately and evaluate them separately. So we can see that this, and this all go to 0. That just leaves 0 over 1, which is 0. And that checks out with what we got using the shortcut. Secondly, we have the limit as x goes to infinity of sine of x. So you might have tried to just plug infinity into here and see what sine of infinity is. But that won't work because sine of x is a repeating wave. What this means is sine always bounces back and forth from +1 to -1. And because this wave goes on forever, sine of x will never settle on a single value as x goes to infinity. It'll just keep bouncing between -1 and +1. This is known as oscillatory behavior, and in cases like these, the limit here does not exist. This applies to trig and all of the repeating functions. And lastly, we have the limit as x goes to infinity of e to the x over ln x. This is not a limit that you can just solve algebraically. We have to look at the graphical behaviors of e to the x and ln x and determine from there what the limit is. So I have e to the x and ln of x on this graph here. We see that while both of them are increasing as x increases, we see that e to the x grows a lot more aggressively than ln of x. Or we can interpret that as the gap here gets bigger and bigger as we increase x. In context of our limit here, this means that our divisor just can't keep up with what we're dividing, so this goes to infinity. This kind of argument is called dominance. We say that because e to the x dominates ln of x, this limit grows to infinity. And if this was reversed, we know that e to the x dominates ln of x, or what we're dividing can't keep up with what we're dividing by, so this limit goes to 0. That's how you evaluate limits at infinity. You'll see them a lot when we do improper integrals and especially when we do infinite series.